Okay, so we're just going to practice showing work on this first one that's about the mean value theorem. They ask us to find the C that satisfies the mean value theorem. Well, since f is a poly, it is polynomial, it's continuous everywhere and differentiable everywhere. So for sure it's continuous on this and differentiable on this. So mean value theorem applies, and there is a C in, there's a C in -1, the open interval, -1 to 3, such that the derivative at that C is equal to f of b. So in this case, it would be f of 3 minus f of -1 over 3 minus a -1. So it means the derivative at C is equal to, well, f when you plug in 3 is 3 squared minus 3 plus 2. So that's 9 minus 3 plus 2. So that is 6 plus 2, which is 8, right? So this is 8. F of -1 is take -1 and square it, minus a -1, plus 2. Well, that becomes a plus. So it's 1 plus 1 plus 2, which is 4, over 4. So this is 4 over 4, which equals 1. So we're trying to find out where the derivative at C is equal to 1. Well, what is the derivative at C? Note the derivative is just 2x minus 1. So derivative at C is 2c minus 1. And so we get that 2c is equal to 2, c is equal to 1. So your answer is A. All right. Next, verify that the function satisfies the hypothesis of the mean value theorem on the interval from 1 to 4. Indicate these hypotheses. So we're going to practice going with these exact instructions. So let me copy those. So if I take all of this and I go this way, let me go copy, done, copy, delete. So here, if I paste up here, so if that's my question, well, first shows that it satisfies hypotheses of the mean value theorem. So part A, it's f is continuous, f is a rational function, so is continuous on its domain everywhere but the point -2. So that's check. And what we needed is, let's see, hypothesis 1. So f is continuous, well, no, let's just do that. So let's just say that one thing. We would also say that also f prime of x is low derivative of high minus high derivative of low over low got squared. The derivative is just what? 2 over x plus 2 squared. So mean value theorem hypotheses are met. F continuous on 1 to 4, check. F differentiable on 1 to 4, open, check. Then part B is find a C that satisfies the conclusion. So the conclusion, mean value theorem satisfied means there exists. Yes, baby.
Can you write ballet dance here?
What? What do you want me to write?
Ballet dance.
Okay, there you go. And then I need you to. There you go.
Thanks.
Awesome. Cool kid. There exists a C in what? There exists a C in 1 to 4 such that. What are we going to say? Such that the derivative at my mystery C is equal to f at 4 minus f at 1 over 4 minus 1. Right? Is that right? So was the last one also? Oh, that was -3. 4 minus. Okay, cool. So, what do we need to show? I need to show f of 4. I need to note that f of 4. Oh yeah, f of 4 is equal to 4 over 4 plus 2. So it's 4 over 6, which is 2/3. I was wondering why it was familiar. I've already done this. 1 over 1 plus 2 is 1/3 over 3. So we have 1/3 divided by 3, which is 1/9. So what we have shown is that we have some point where the derivative at C is equal to 1/9, but the derivative for our function we said was 2 over x plus 2 squared means that 2 over c plus 2 squared is equal to 1/9. But that means that 18 is equal to c plus 2 squared because we cross multiply. Plus minus root 18 is equal to c plus 2. In other words, c is equal to -2 plus or minus root 18. So c is equal to -2 plus root 18 is the only one that's going to be in our interval. Yes?
Do you like dark chocolate or grizzly bear brown
Dark chocolate. Good call. Sorry, helping her do some coloring. So awesome. Great work. That's the only one that's in our interval. It says give a geometric interp of the mean value theorem. Sketch the graph of the function on the interval and indicate the corresponding secant and tangent lines as well as C in your diagram. So really what it's saying for part C is, do you realize, so that's, I'm going to put part C right here. So for part C, it's saying, do you realize, part C, that if our function is x over x plus 2, it means that there is going to be from 1 to 2, let's see, okay, so -2 is where our, this thing, x over x plus 2 is going to have a vertical asymptote, -2, so it's going to look something like this. And so if we're going from 1 to 4, here's 1 and here's 4, maybe I make it look a little more pronounced. Because what I'm really trying to show is just the fact that I've got a secant line. Oh man, I wish I could make it look a little better. Let's see. What am I trying to do? I'm trying to get it so it's flat enough, but not too flat. So I guess what I need is I need to turn a little sharper.
Dad, you're doing something and you don't even know what you're doing?
Okay, that hurt. Yeah.
Just pointing out that it's a little funny.
I know, shots fired. Okay, so if maybe I've got something like this and something like this. So, boop, boop, boop. So maybe this is like 1 and this is 4. If we've got a, make it red, got a secant line that looks like this and goes through the 2 points, there is some point C somewhere in between those 2 points, somewhere inside the interval where the slope of the tangent line is equal to the slope of the secant line. They've got to be parallel. That's all you're trying to show, yes? Okay. Cool. So then give a geometric interp of the mean value theorem. That's what we did. Cool. So on your test tomorrow, I may not ask for the part C, but that's definitely possible for your final. So don't freak out right now. If we don't know how to do that, we will practice more and more about that as we go along. But this is definitely testable. Okay, so let's go back. Then the last one we had is find this absolute min or max on an interval. So I'm going to say done, copy, delete. Let me go here, do one after it. Okay. All right, find absolute min and max on an interval. So f, so f is continuous on the closed and bounded interval. So since it's continuous on this closed interval, that means, oh, maybe I put since f is continuous on the closed, comma, extreme value theorem applies, which means we can find an absolute max somewhere in that interval. So step one, let's find the critical values, which is where the derivative equals 0 or that derivative is undefined. Don't forget about your or. So I take the derivative, and the derivative here is 27 minus 3x squared. Where is it equal to 0? Well, more importantly, where is it undefined? Absolutely nowhere. So that's easy. Nowhere because it's a polynomial. But then derivative equal to 0 would be 27 minus 3x squared equals to 0. 3x squared is equal to 27. Yes.
To me, you're talking nonsense.
To you, I'm talking nonsense. Well, I totally agree. Sometimes it can sound that way. So plus minus 3 is x. So what does that mean? Step 2, those are the only places where I could have critical values. But notice. Got to be careful. This is plus or minus 3, but only critical value is x equal to 3 because it's in the interval. So the only critical value in 1 to 4 is x is equal to 3. The other one's outside of it. So step 2 is to take f of our critical values and f of our endpoints. So f of 3 is one thing I'm going to do. So bloop, I'm going to do f of 3, and I'm also going to do f of 1 and f of 4. But remember that my function is 10 plus 27 minus, I think, squared. This is 10 plus 27 minus 1. It's going to be 10 plus 27, plus 4 minus?
10 plus 27 is
You do.
37.
Good job.
Because you just go to the next row.
Oh, that's good.
So let me,
Oh, it's all good. So this should be cute. No, it's okay, Eleanor. I got it. But thank you, though. I really appreciate it. Oh, there's some paper over here if you need it. There's some Post-its if you need it. So what I've got right here.
So I'm going to show you.
Okay, so it's 37 minus 1 is 36. This one is 37.
27.
16 times 4 is 64. So this is what? What was that? Oh, it's in. This would be 27 times 4. Sorry, that looks a little weird. Okay, Eleanor. Yeah, just leave that paper here because I got to talk to these kids. Yeah, thank you. Oh, cool. Thank you.
So you have 20.
Just 1 minute. Yeah, you can tell me in just a minute, okay? Hold on to that thought. Thank you, sweetheart. So, this is 10 plus 4 27s. So 27 is 4.
427.
Right, right. So that's 108. And this is minus 64. So that would be what? 118 minus 64 gives you a 4 and a 5. So this one is 54, right? So I've got 54 here. I've got 36 there. And up here, 27 times 3 is what? 81, right? Which makes sense because I'm awake. So that's 91 minus 27. So 91 minus 27 is 11. 4 and 6 is 64. So it seems like that's going to be the absolute max. This is the absolute min. So absolute max is f of 3 is equal to 64. Absolute min is f of what? F of 1 equals 36. Cool. And that's how we'd write it. Good work. So that's 12. So we've done, what, 7, 8, 12. We've shown all our work. Then we move on to this. Okay, so find the linear approximation of this function near a is equal to 1. Well, anytime you see linear approximation, you know that that just means tangent line, because the line becomes an approximation to the function. So y minus y1 is equal to m x minus x1. And so, in this case, x1 is equal to a. So it's m x minus 1. Here's y minus 1. Well, y1 is just equal to f of x1. So in this case, it's f of 1, which equals natural log of 1, which is equal to 0. So y1 is 0. Why did I put that as 1? It is 0. Right? So we go over to here. But then we also note, this is my scratch work over here, I also know that my derivative is 1 over x. So that means that my derivative at 1, which is my slope, is just equal to 1. So this is y minus 0 is equal to 1, x minus 1. In other words, y is equal to x minus 1 is the equation of my tangent line, or in other words, my linear approximation. So what I've just shown, since that's my linear approximation, so the natural log of x can be approximated by my linear approximation near x equals to 1. So as long as you are near the value of 1, natural log is approximated by x minus 1. So use it to estimate this. Natural log of 0.98 is going to be approximated by 0.98 minus 1. But that's just equal to what? 0.98 tens hundredths. That's 2 hundredths. So that's negative 0.02. Boop, 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 boop.
Hey,
Yes.
they actually, all of the crayons and colored pencils in here.
That's our
actually
estimate.
say the colors of actually say the names of the colors, but the markers, for some reason, do not.
Didn't know that. So that's negative 0.02. Very cool.
They don't know.
So it says, is the answer an underestimate or overestimate? Draw a picture to justify your answer. Well, because, put my picture right here, because I know that the natural log of x looks like this. And I know that the natural log of 1 is 0, natural log of x, then the tangent line is going to look something like this. And so that means, boop, maybe I draw it like this. So that means back here at 0.98, my approximation is going to be above my graph, so it's going to be an overestimate. It's an overestimate. Partially because the second derivative is second derivative at 1 is negative, right? So because that second derivative is negative, not just at 1, but everywhere around there, that's really what's killing it. Okay. Let's do another one. Linear approximation of this thing at 1. Holy cow. Sorry, 628. So if I do this linear approximation, again, it's going to be y minus y1 is equal to m x minus x1. Because linear approximation, I'm just thinking tangent line. And really that line approximates the curve. So this is x minus 1, m. This is y minus y1. Well, if I do f of 1, that's going to be my y1. Yes, baby. Cool. Oh, that's really cool. That's really, really good. Save that. That's really good. Good job. Can I keep it?
Sure.
That's really good. Oh, don't fold it. That's really good. Thank you. That's really nice. So here we're going to do y minus 1 is equal to, and m is just my derivative at 1. But, yeah, my derivative is 1/3 x to the negative 2/3.
Get something for me to draw.
Draw me a tree.
Got it.
Awesome. Is 1/3 x to the negative 2/3. Because when I see this, I just see x to the 1/3. So, that means my derivative.
You want to sketch with no colors?
Correct.
No colors.
Yep. So f prime at 1 just means we're going to do 1/3. If I do,
Regular pencil?
please. If I do 1/3, I'm just going to plug in 1.
Just want the black.
So it's going to be 1 to the negative 2.
Black color.
Cool, thank you. So that's 1/3. Got it? So my slope is 1/3. I can come over here. It's 1/3 x minus 1. So what do you get? You get y is equal to 1. Sorry if that's not easy to read. That's 1/3. That's 1 plus 1/3 x minus 1. And so that is our linear approximation. So if I want to make that look a little nicer, I would say, look, that's 1 plus 1/3 x minus 1/3. So really your function is just, my function is just what? 1/3 x plus 2/3. So the cube root of x can be approximated by the linear function 1/3 x plus 2/3 as long as you are near x equals 1. That's why it's a linear approximation, because the line is approximately the graph, as long as you're near 1. So use it to approximate this. Well, what we're saying is that the cube root of 0.97 is approximately 1/3 0.97 plus 2/3. Yeah, it's perfect. Thank you. I really like it.
I'll put in some color.
Oh, okay, cool. And so I think when we worked this out earlier, we found out that this turned out to be like 99 over 100. But yeah, you can simplify that algebraically if you want to. Cool. Oh, hey, guess what? I'll show you how to do that. So this is going to end up being, it's pretty obvious, right? This is 2.97 over 3. And you could leave it that way, that's fine. 99 over 100. So when we see this, wants to know what is an overestimate or underestimate. Well, because I know that the graph of the cube root of x looks this way, and I must have my parent functions memorized, I know that at 1, tangent line is going to look like this. So if you go over here at 0.97, again, it's going to be above the graph, so it's going to be an overestimate. It's an overestimate. Cool. Great work. Was there anything else I need to do? Okay. So set a timer for 10 minutes.
10 minutes, starting now.
Okay. I gotta go get my kid here in a minute. So let's do this one. Find intervals where this is increasing or decreasing. Thank goodness they give us the function, the first derivative, and the second derivative. So I know if I'm talking about increasing or decreasing, I'm talking about f prime. Yes.
With the leaves, do you want evergreen or emerald?
Evergreen, please. Step 1 is critical values, which means the derivative is equal to 0 or derivative is undefined. So take my derivative. I take my derivative, which is this. Boop, boop. 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 Squared. Yes.
Green for the grass. Evergreen or emerald?
Oh, I said evergreen, please.
No, for the grass.
Oh, emerald. Derivative undefined.
Yes.
Thank you.
I love emerald.
It's undefined nowhere because it's a polynomial if you were to multiply it out. Over here, equal to 0 is going to be this,
For the grass.
x minus 2. So either this equals 0 or this equals 0. So you're going to end up getting a half or 2, right? So if I get a half or 2, those are my two critical values. Then step 2 is to partition. So it means I take my entire number line and break it into pieces by using 1/2 and 2. So I get my 3 intervals. And so step 3 is my chart. So I'm going to go from negative infinity to 1/2, 1/2 to 2, and then 2 to infinity. Blammo, whoops, blammo, blammo. And then I put my factors up here. So make sure, no matter what, all the factors of your derivative, no matter what it says over here or over here, all the factors of your derivative, or, yes, let's go in here.
Dark chocolate or grizzly bear?
Grizzly bear, please.
Yeah, grizzly bear is really light, so I think that's the perfect thing for the trunk
Good call.
of the tree.
Yep. So great thing. This is always going to be positive because it's something squared. Over here, I think of something really big negative. That's going to make 4 times really big negative minus 2 negative. In here, I pick out a number like 1. 4 times 1 minus 2 is a positive. And if I have a really big positive in this interval, I've got a positive. So that should tell me about my derivative. This times this is going to give me a negative, which means f is increasing. Here I get, oh, poop, seriously? I meant decreasing. Over here, plus, get increasing. Over here, I also get plus, which is increasing. And that makes sense, does it? It's a cubic, it's going to go like this. Should be, wait, does that make sense? This is a 4th degree, but it's going to have, so 4th degree is going to be up like this. It's going to have these zeros. So it's going to be, does that make
Dad, do
sense?
you want this tree to be in the summer or the spring?
Summer, please.
Okay.
Yeah, it should make sense. Okay. So let's look at, oh, then it wants me to find local mins and local maxes. So I say that the first derivative changes sign from negative to plus at x is equal to 1/2 implies that f has a local minimum. F changes sign from positive to negative at x. So, and then there are none of those, right? And there are none. So just one sign change. Cool. Let's double check that with x minus 2 cubed over here. So go over to here. X times x minus 2 cubed. And so what did they say we had? They say that we had some decreasing, increasing, and increasing. Yeah, that makes sense. Thank you. Oh, really great picture. Thank you. Thank you.
What now?
Oh, well, if you just want to get ready to go here in just a second, there's my half, and that makes complete sense.
What should
Yes.
I draw now?
I will just hold on just a minute and let me finish up here.
I'll
And
draw
we'll
a
talk.
rainbow.
Also, good choice. Solid choice. So 1/2 and 2 were our only points. Here you see that there's my 1/2. There's my 2. I'm decreasing, then I'm increasing and increasing. So yes, it is perfect, just like our work. Okay, so then for intervals of concavity,
Perfect.
yep, step
I
one.
just say it was perfect. Nothing's perfect.
Nothing's perfect. Thanks, Eleanor. Critical value. But in this case, we're talking about the second derivative, where the second derivative is equal to 0 or undefined. So, second derivative that they give us is 12x minus 1x minus 2. So what that's really telling you is, where is it equal to 0? Where is it undefined? Well, it's undefined nowhere, because it's a polynomial if you multiply it all out. Where is it equal to 0? Well, I've got 12x minus 1, x minus 2. Where's 12 equal to 0? Nowhere. X minus 1 equal to 0? Here. X minus 2 equal to 0? Here. So I have two critical values in this concavity conversation.
Cavity.
Yep. Okay. So then, no, not like a tooth cavity. So step 2 is to
I was about to say,
partition.
what?
No, you do not have cavities, Eleanor. 1, 2. And so then step 3 is to chart. So for our chart, I can now read off my intervals from here to 1, 1 to 2, 2 to infinity. I made 2 cuts. I get 3 intervals. Boop, 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 boop. Okay. And so now, 12, I'll just make that one whole piece. This, x minus 2, should tell me about my second derivative, which is going to tell me about f. So if I'm really big negative, this is going to be negative, this is going to be negative. If I'm really big positive, this is positive, this is positive. If I'm at 1.5, this is positive, and this is negative. So it looks like my second derivative is going to go positive, negative, positive, which is concave up, concave down, and concave up. And it looks like f double prime changes sign at x is equal to what? 1 and 2 implies boop, 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 inflection point. 1 and 2. Cool. Great work. Well, I'm going to stop there. We're going to finish this little bit that we have left to do. So we've got one question, a couple graphs. We'll do it in a minute.